Good afternoon, everyone. Welcome to Building Matters, the webinar series organized by the City of Richmond's Buildings Department. My name is Sefer Forushani, and it is my pleasure to introduce our distinguished speaker today, Professor Kevin Gurney. Kevin is an atmospheric scientist, ecologist, and policy expert currently working at the School of Informatics, Computing, and Cyber Systems at Northern Arizona University. Professor Gurney's research involves simulation of the global carbon cycle using the inverse approach, linkages between terrestrial carbon exchange and climate variability, deforestation, and carbon-climate feedbacks. Most recently, he's been working on fossil fuel CO2 emissions at global, national, and urban scales. Professor Gurney is an IPCC lead author, a National Science Foundation Career Award recipient, Sigma G Young Scientist recipient, a Fulbright scholar, and has published more than 140 peer-reviewed scientific articles. He's also the author of a book by MIT Press called Mending the Ozone Hole. It is my pleasure to welcome Professor Gurney to Building Matters, and with that, I hand it over to him. Professor Gurney, please take it away.
Done obviously at the country level by almost all countries around the planet now as part of the UN Framework for Climate Change Convention. It's obviously done at the country level. It tends to be, a relatively simple counting up of fluxes traced to energy consumption, primarily CO2, but methane and N2O are quantified along with a lot of the other gases. But a lot of the focus is on energy flows within countries and attempting to count that up and turn it into the UNFCCC. But there was a lot of forces that were pushing those of us in the academic community that were interested in this problem towards tackling this in a really different way, rather than these sort of, I should say, kind of counting up systems in inventories. There was interest of using the atmosphere and a bunch of other measurement assets to both not only improve how we do the quantification, but change its nature in terms of its space-time detail. And a lot of that really came out of the evolution of the negotiating process. On the left-hand side of this figure, I'm showing a report that actually came from the National Research Council, in which they emphasized, this was in 2010, emphasized the need to really verify emissions. That it wasn't enough to just do these bottom-up inventories, but we need some independent means to verify those accounts. And verification has always been a very, very tricky subject within international negotiations, just because it tends to set off a lot of alarm bells amongst countries in terms of control and provenance over their own data. And so it's always been difficult to discuss. But nonetheless, within the negotiating process, and on the right-hand side, I'm just showing an evolution from Kyoto in 1997, Bonn in the year 2000, and then Copenhagen in 2010, that slowly through this evolution more and more, there was at least a tacit interest and recognition anyway that verification was important, and that we probably needed to use a variety of different tools to get at quantification of emissions. Another big force within the scientific community that was pushing us towards a bigger and more complex information system was the fact that over time we've been observing CO2 in the atmosphere at greater and greater density with a more diverse platform of technologies. The traditional technique was flask sampling that was really actually only at a few places around the planet. Started in 1957. It's the backbone of the very famous curve, probably many of you have seen, of CO2 rising at the South Pole and Mauna Loa. But that system has increased, and now there's lots and lots of stations around the planet, aircraft assets, and so on and so forth. It's still not as dense as we would like it, but that density was beginning to suggest a slightly different system. And along with that ground-based observing strategy, the emergence now of remotely sent CO2 has significantly added to our ability to measure CO2 in the atmosphere. And an instrument that was put up by the U.S., the orbiting Carbon Observatory. Number 2 was launched in July 2014. Actually, number 1 failed, did not make it into orbit. Number 2 was launched in 2014, and now OCO3, the Orbiting Carbon Observatory 3, was launched in 2019. And it was important because it looks at the surface in these, relatively small pixels of information, looking for, this is designed to do CO2, looking for the spectral signature of carbon dioxide. And that also put a lot of pressure on, building a new system, in the sense that we could now observe atmospheric CO2, both from the ground with aircraft and now with satellites, at pretty high resolution all across the planet. Whoops, sorry, I'm trying to show a movie here. Try again, yeah. Hopefully you'll see a sort of what looks like weather systems moving around the planet. And that kind of makes sense, because CO2, when you really look at it on the planet, just looks like weather. It's obviously emanating from the 3 big bullseyes on the planet where there's lots of industrial activity. Let me run that again. And then it essentially gets transported around the planet. It's a passive tracer. It just acts like, almost like air, in that it just flows around the planet. And that suggests that with that level of complex atmospheric CO2 merged with this denser observing system, leads to a lot of potential to do a lot of science. The final force, I would say, aside from the previous mentioned, is the fact that there were changing policy needs. We knew verification was important. We now have more and more assets to observe CO2 in the atmosphere. And lo and behold, policy by the end of the 2000s was beginning to really migrate from not just focused on nation states, but starting to focus on cities. Cities became important leaders in articulating both the challenge and responding. Many cities, as a lot of you know, have really stepped out trying to take the lead on mitigating greenhouse gas emissions, and indeed are now part of the international process, though as an informal player. And I just put some examples of that. This really came to a head, I would say, in Copenhagen in 2010. Down the lower left is California's important effort at the state level, which is now a few years under their belt. And then just the fact that many mayors and cities across the planet have pledged to reduce their emissions and have indeed begun to do so. And it's also important to remember that cities account for something like 2/3, maybe 65 to 75% of the energy-related carbon emissions on the planet. That shouldn't come as a complete surprise. It's where most of the people live in the world. We're now effectively an urban planet. We passed over the 50% mark a few years back, and that's only going to increase. The planet will become more and more urban with a greater concentration of population in urban areas. Urban areas are going to triple by 2030, and urbanization trends are doubling by 2050. So this will only increase, and hence cities are clearly important players in tackling climate change. Finally was the issue of uncertainty. And again, coming from the academic community, this was how we used to quantify emissions around the planet sort of back in the 1990s, mainly for scientific purposes. This wasn't reported to the UN. This was just something that scientists did to try to solve aspects of the global carbon cycle. And that looks like a pretty good map. It seems to be pretty detailed. But if I were to zoom in on the US, this is what it would look like. And it was really just fossil fuel CO2 distributed into these 1-degree boxes, which is about 1,000 kilometers on a side. 100 kilometers on a side, forgive me, on an annual basis. And it was pretty simple. The distribution was just where basically population existed, which of course you might wonder, about things like interstate highways and the fact that power plants aren't really where people live. And it was clear anyway that the inventories we were using for scientific purposes just were not really up to the task that we needed them to be up to, both because of all those policy forces, because of the measurement density, it was clear that we needed to do a much, much better job at building this information than we had in the past. So that really started to set up what we think of as the requirements for a new system. We knew it had to be pretty granular, and by that I mean high resolution. So we need to isolate pretty small boxes at the surface and understand the emissions in a much, much more detail than we had in the past. We need those emissions to be linked to the atmosphere, and by that I mean we need to be able to have fluxes that get mixed into the atmosphere that can then be measured through either satellites or instrumentation, because those measurements don't measure fluxes, that is the amount of mass leaving the surface. They measure a concentration in the air. Those two things are pretty different, but you can connect them, and that linkage is crucial. The information had to include process. So it isn't just how much is being emitted, at a particular place, but what is it? Is it a car? Is it a factory? Is it a building? What's giving rise to the emissions? And finally, we needed transparent, traceable measurements to independent scientific standards that are methodologically consistent. So a pretty high set of demands on what we considered a new CO2 information system. So my group, back starting in the probably early to mid-2000s, began to quantify CO2 in a variety of different scales. This is our global scale data product called the Fossil Fuel Data Assimilation System. It's done a lot with remote sensing, although we use ground-up information as well. We do a 1 kilometer spatial resolution, the whole planet, every hour for about 18 years now. It's not that accurate just because we're at a relatively coarse scale, but it's important as a global data product, and it is consistent with the nation state account. The next effort we engaged in was doing this sort of the same thing for the U.S. landscape. This is called VULCAN. Originally, it was built, published in 2009. It tackled the U.S. landscape wall to wall at about 10 kilometers by 10 kilometers every hour for the year 2002. It was built purely from the bottom up, so this uses no remote sensing, nor does it use any atmospheric measurements. It's a pure engineering approach, much like what cities will do on their own right now, systematically with a bunch of different data sets. That's now been drastically updated. It's still at about half a kilometer or so on a side every hour. We now have a data product that runs from 2010 to 2015. We're currently updating that to be up to about 2019. In fact, we're even working on getting it into real time. It is what's referred to as a Scope 1 inventory, that is territorial or only direct emissions, that is emissions coming out of a piece of landscape due to the combustion of fuel. But we're working on, in fact, we already have a Scope 2 data product. That means that the emissions from a power plant, which in this system are placed at the power plant, are now in Scope 2 allocated to the place where that electricity is consumed. And indeed, we're even working on Scope 3, which allocates all demand for goods and services from the factories and the commercial buildings where the emissions occur to where the products are being consumed. A much more difficult task that we're working on, we'll have done probably in 2 or 3 years. So this is the latest VULCAN. It's called version 3. It's publicly available. Anybody can download it, use it. And indeed, it forms a basis for how we carved out cities that I'll get to towards the end of the talk. All right, so here's some examples. If I were to carve out cities from VULCAN, this is what they would look like. This is done at 1 kilometer. But again, it's enough to actually see an awful lot of detail. This is Chicago all the way up to Milwaukee. You see Madison in the upper left. This is the San Francisco Bay Area, including Sacramento, Stockton, Modesto. This is the Houston area, Beaumont to the right, Port Arthur to the right, Galveston there on the Gulf Coast. This is Boston and the surrounding areas all the way out to Springfield and Hartford, Connecticut, all the way down to New Haven, and of course Providence, Rhode Island. And this is the New York, Philadelphia, Providence kind of corridor on the east coast of the United States. And then finally Washington, D.C. and Baltimore corridor in the sort of mid-Atlantic area of the eastern United States. Now, those cities, just to put another emphasis on how important cities are, if we take the top 50 cities in the United States, they are effectively the third country on the planet. Only the United States in total and China have a greater amount of greenhouse gas emissions than do the top 50 cities in just the U.S., not the world, just the U.S. Top 20 cities in the U.S. rank as if they were the fifth, top 10 as if they were the seventh, and even the top 5 U.S. cities still rank just within the top 10, just behind the country of Iran and ahead of South Korea. So this just emphasizes the fact that cities really, really matter, and hence doing quantification within the urban environment is important, both because it accounts for a lot of emissions and because they've taken such an important step forward in quantifying emissions. This last data product goes into individual cities in tremendous detail. We've only done this for 5 cities in the United States. We have not done this for the whole U.S. landscape. VULCAN has done it at about a half a kilometer. This goes into an individual city down to the building scale. These are the roads here, the major roads, and traffic during the day. This data product is called Hestia, as opposed to VULCAN. VULCAN's the Roman god of fire. Hestia is the Greek goddess of the hearth fire. You can see now the red buildings here are the commercial sector, the green is the residential sector, and then these aprons, these purple aprons, are the roads. So we can put it all together and we can actually see the evolution of the urban environment through the day. Let me run that again, where you see people waking up in the suburbs, getting onto the roads, moving down towards the center of the city. This is the city of Indianapolis, the first city we did in the Hestia effort, and I'll show you in a minute some of the other cities we've done. So Indianapolis is in the upper left. We've accomplished the full Hestia data product for that city, and we've linked it to measurements in the atmosphere. We've instrumented 11 cell towers with very expensive monitoring instruments, about $100,000 each, that measure CO2, methane, CO. We also fly aircraft over the city, measuring CO2 and methane from a downward-looking instrument. In the bottom lower left there is the city of Baltimore. We've also done a building level treatment there. The upper right is Salt Lake City. And then the largest domain we've done so far is the entire LA megacity domain, which is about 80 cities in 5 counties, very large, almost 20 million people. And then we're currently working on the Washington, D.C., all the way up to Baltimore corridor and some surrounding counties there. We have colleagues doing some similar style work in Boston, in Toronto in Canada, in Paris, and then some really early work that we're involved with in Sao Paulo in Brazil, Melbourne, Australia, and Auckland, New Zealand. So we're trying to expand this type of approach outside the U.S. where it's been pioneered to other parts of the world. And I should pause a moment and just say that though I don't go into a lot of methods here, I can certainly do it in Q&A, but just simply stated, our methods break down the fossil fuel CO2 problem basically into 10 problems. We tackle each sector separately. In the VULCAN system, which is the whole U.S. landscape, we're mining a lot of federal data. So all of the traffic data that's monitored across the United States, all the VMT data that goes with that, vehicle miles traveled. We get the data from every single power plant. Many of those are direct flux monitoring instruments that are sitting in the stacks. We're using a lot of carbon monoxide emissions reporting, which is part of the air quality system in the U.S. It's been reporting for 5 decades. Lots of census data, data on buildings. We'll mine, tax assessor parcel data so that we know about every single built structure in the U.S., so on and so forth. Very, very detailed sort of data mining exercise to try to capture emissions. And of course, we're mining all the energy data that's available. In the U.S., it's actually quite a bit. And then in Hestia, that's very detailed city-level treatment. There, we're just mining additional local data. It is not necessarily available at larger scale, to state, provincial, or federal level, but is uniquely local. We'll mine that, combine it with what we have in Vulcan, and actually nest Hestia within Vulcan so that the two conserve mass and are internally consistent. So with that pause out of the way, I'll jump back to this slide, in which I'm just trying to emphasize again what you get for all this granularity. You know, many of the self-reported inventories that cities make themselves are typically whole cities that might identify a sector. The advantage of getting down into the high level of granularity is on the left is just a cumulative plot of on-road emissions. And what it shows is that 10% of the 100-meter grid cells in the LA, and this is just LA County, account for 60% of the on-road emissions. In other words, fossil fuel emissions in scientific parlance are extremely log normal, that a few large things tend to account for the majority of emissions, and then there's lots and lots of little things. That means that if you're going to tackle a city and you want to really be efficient and prioritize emissions, you need to know where those emissions are so that you can effectively isolate them and go after them rather than tackling the whole city in one fell swoop. This is just to emphasize this now sequence that we have. This is the example of Indianapolis, where really we have our Hestia fluxes in the upper left. That's super detailed inventory. We actually transport that through the atmosphere with an atmospheric transport model, connect that to measurements on cell towers and aircraft, and make sure that what we measure in the atmosphere and what we emit at the surface are internally consistent. That is incredibly important because that offers us that very key bit of verification that we know that the emissions we're creating indeed are correct to the atmosphere, which is probably the most accurate way to measure the system. Okay, so we've done some of that assessment. This is a paper that was written last year in the proceedings of the National Academy of Sciences, in which we compared a very unique atmospheric CO2 measurement that uses radioisotope CO2 to our Vulcan data product. They agreed to it 1.5%, so very, very close to what the atmosphere sees. In the city of Indianapolis, we did a very detailed comparison of Hestia inventory there to a very dense atmospheric monitoring network. There we were within 3%. So pretty accurate in these two cases, which gave us a lot of confidence that what we were building from the bottom up was, on track and doing the right thing. Now this brings me to the study that, it spawned your invitation for me to come here, which is that once, now that we've built both Vulcan and Hestia, although this really uses Vulcan, and we gained a lot of the confidence in Vulcan by comparing it to the atmosphere, we decided to begin to compare it to self-reported inventories, in U.S. cities. And though many cities have done inventories, we found 48 that we had really adequate documentation in which we could really fairly compare what we get in Vulcan to what the city reports. And in Vulcan, all we do is carve out the governance boundary of the city and then compare our results to the self-reported inventories. We ensure that we're only using scope 1 versus scope 1 since cities do a mixture of scopes, and we ensure that a whole sector is present or we don't do a comparison at all. And what we found is that the two are pretty different. The mean difference is about 18–19%. The mean absolute difference, that is without the sign, to some some underestimated compared to Vulcan, some over-reported. When you take them all at absolute values, about 30%, but the range is enormous. It goes from 60% overestimate all the way to 150% underestimate in some cities. So quite a range. And some cities are very close. Whether that's being close for the right reasons or for the wrong reasons, hard for us to say. This just shows our 48 cities. When you put them up against all the cities in the U.S., since we have the entire landscape, we're able to plot that. The blue line is just the cumulative emissions as a percent, and the red line is just the log of emissions by rank. And you can see the 48 cities that we did capture, really do occupy a pretty upper end of cities in the U.S., although we have some at the medium and even small size as well. So a reasonable range of city typology. Now, as we move forward, we're fully aware that Scope 1, which is the comparison we've done thus far, is not the only thing that cities care about. Scope 2 and Scope 3 are very important. Again, Scope 2 is electricity allocated to the consumption point, because in a city, that can be very, very distinct from the emissions from a power plant. Power plant may service lots of areas, and so Scope 2 is important. We have that data product, we just haven't made it public yet. And we are indeed working on Scope 3, as I said, I think previously. It'll be out in a year or two. And independent verification, that's going to be hard, but we're working on that actively. We've also built a real-time data product. It's not granular, it's the entire U.S., but we're able to estimate emissions for the U.S. up to last week. We've done some comparison to COVID. I won't bother you with this rather complicated-looking plot in the lower right. It's actually a phase diagram. It just shows that a lot of the lockdown behavior and emissions have gone hand in hand, no surprise there, and primarily on-road and aircraft jet fuel has been the driver there, although there's some reduction in electricity and a little bit in the industrial sector, though it's lagged quite heavily from the lockdown orders. And finally, as I sort of intimated when I was talking about the Hestia Data product, we're trying to expand this to cities around the planet. We're working with an international consortium of scientists. I've mentioned some of the principles here on this integrated greenhouse gas information system that, again, uses satellites, local data to try to do this thing in cities all around the world and indeed build a coherent, systematic way of doing this. And then I'll make one last appeal that we look at that system very much as an analog to weather forecasting in much the same way that one would not expect an individual city to collect weather data, run a weather model, and generate their own weather. It does seem not necessarily the best approach for each city to do their own greenhouse gas inventory. We can save them a lot of time and a lot of trouble, allow them to focus on the most important thing, which is mitigation, something they can only do that we can't do, through, again, a very large system that can do all cities collectively at once and deliver that information to cities effectively at no cost. Since we can do this with, again, with pooled resources. In the U.S., we've done it with taxpayer money to do the research we've done thus far. So that's the model we're aiming at. It's not in place yet, but we're appealing to the U.S. federal government to champion this system and indeed make a federated system around the planet such that landscapes everywhere can be completely covered by monitoring and greenhouse gas flux estimation. And with that, I'll stop. Sorry about the glitches at the beginning. I'm just going to thank some of my funders here that have supported this work and all the members of my group that have done most of the work. I'm just the guy that gets to talk about it. So thanks a lot.